Good morning, everyone. Today we are looking at your questions on acids and bases. But first, I want to remind you to send us questions. Now, if you've got questions, you can send it to us at junior.tukkie@up.ac.za. And then we will discuss it either in a session like this, or we have a whole team of students at the Junior Tukkies who want to answer your questions. So today we are going to look at questions on acids and bases. And the first question is one where someone asked us to look at November 28 paper number 1.7 of the multiple choice questions. Now, I always find multiple choice questions are very good questions to see if you really understand the work, right? So if we look at this one, it says the reaction 1 and 2 below have equilibrium constant Kc is greater than 1. So immediately, this is not only about acids and bases, this is definitely about equilibrium as well. And they give you a Kc bigger than 1. Now, what do we know if the Kc value is bigger than 1? Now, remember the Kc value is products divided by reactants. So if it's product divided by reactants and you get something bigger than 1, it tells you there's more of the chemicals in the product stage than in the reaction stage. Remember, it's a ratio. You have to talk about both, right? So there's more of the products than of the reactants, and therefore you get a bigger number than 1. Right, now that was what they gave us, and now they asked us, based on these reactions above, the acids in order of increasing strength, right? So they want to know which is the stronger one. Now, what do we know about an acid? An acid is a proton donor, right? Now, if you look at this first one, in the forward reaction, H3A is your acid because it's donating a proton. I can see it's giving off a proton. So that will be what we call the conjugated base, right? And in this one, that will be your base because it is receiving an H+, and that will be my conjugated acid. So if we consider this first one, you've got two acids. You've got H3X and you've got H2CO3. And now to determine which one is stronger, we're looking at that Kc. That Kc that's bigger tells me that the forward reaction is happening more completely than the reverse reaction, right? The forward reaction is making more products than the reverse reaction. And that tells me H3X is stronger than H2CO3. It's a stronger acid than H2CO3. Looking at the next one, well, you've got H3O plus, the hydronium ion, and you've got water over there. So this is definitely the acid because it's giving off a proton, right? And that will then therefore be the conjugated base, right? Acid go with the conjugated base and the base with the conjugated acid. Right, and over here, this will be the base. We know that because it's receiving a proton, right? And then that will be my conjugated acid. So here, the acids are the hydronium ion and H3X. And now, once again, with a Kc bigger than 1, it tells you that the acid acting in the forward reaction is stronger than the acid acting in the reverse reaction. So this second part actually tells me that H3O plus is stronger than the H3X, right? So if I look at increasing strength, if I look at the stronger one, well, you've got H3X, and the first equation told me that H3X is stronger than H2CO3, and the second one told me that H3O plus is stronger than HX. So from weakest to strongest with increasing strength, it will be the carbonic acid and then H3X and then the hydronium ion. Right, guys? Now, we are going to do some more multiple choice questions because that's so nice to know if you understand your work. So let's start with the first one here, and that is quite an easy one. The two substances that act as acids, right? So in the forward reaction, that would be water because it's giving off an H+, a proton. And in the reverse reaction, that will be that NH4 plus, because that is giving off an electron in the reverse reaction. So you've got your acid, you've got your conjugated base, right? And this is the base and the conjugated acid. So definitely the two acids are water and the ammonium ion. Right, next up. Which one of the following ions or compounds is an ampholyte? What do we know about an ampholyte? That's something that can act as both a base and an acid. Right, so it needs to be able to give off an H plus and to receive an H plus. And immediately the first two will not be able to act as acids. They don't have a proton, they don't have an H plus to donate. So they are definitely not the answer. And with the last one, the carbonic acid, it won't receive an H plus, it can only give off. So the only one there that can be an ampholyte is HCO3 minus. Right, moving on. Which of the following solutions with water will have the smaller, a pH smaller than 7? Immediately it tells you it must be acidic. Right, so we're looking for the acidic solution. First one there, sodium hydroxide, I know that is a strong base, so that will definitely not be acidic. So that one I can leave out. Now let's think about the others. They are all salts, and salts will hydrolyze when they get into water. And when they hydrolyze, it means react with the water. They can produce hydronium ions, which makes the water acidic, or hydroxide ions that make the water basic. Right, now to understand that, let's just think quickly about HCl. What we know about HCl is that is a strong acid. And with a strong acid, we know it ionizes completely. So this will react with water and it will give you Cl minus and H3O plus. Right, and it ionizes completely. So every single molecule will go over. It prefers to be in that state and not in this state, right? Now, if that is the acid, then this one we call the conjugated base, right? That can do the reverse reaction. But if the acid is strong, it wants to ionize, and that means the conjugated base is weak because that will not go back, right? Because this one preferred to be Cl minus. And that's what we're going to use when we look at the ions. Now let's take the first one there. We have sodium ions and we have chloride ions. Now, where can the sodium come from? That could have been from sodium hydroxide, or it could form sodium hydroxide, but what do we know? That is a strong base and it will choose to be dissociated. So this one will not hydrolyze, right? So it will not react with water. How about the Cl minus? Right, that comes from HCl, which is a strong acid. It wants to ionize, it wants to be Cl minus. It is not going to go back, right? So the conjugated base of that strong acid is a weak base. It won't react. So this one we will end up with a a neutral solution, right? You can also have said, I can prepare sodium chloride solution by adding sodium hydroxide and HCl and doing substitution, right? Double substitution will end up with sodium chloride. And this is a strong base and this is a strong acid, and therefore it will end with a neutral solution, right? Second one. Now we're not looking for neutral, we're looking for acidic, right? Second one, we've got sodium ions and we've also got carbonate ions, 2 minus there. Right, so what do we know about sodium? That will remind us of sodium hydroxide, and I could also have used H2CO3, the carbonic acid. Those two together will react to give me a solution of this. And this is a strong base, and that is a weak acid, right? So immediately it tells me the final solution will be basic. So you can go back and think what acid and what base we could have used to prepare that. That's one way to do this. But you also need to be able to explain how it makes the solution basic. So there we will say the strong one prefers to be dissociated, right? The strong base prefers to be dissociated. So this will not go back to Na. It will stay like this because this is the preferred form. Let's go to that one. The weak one does not want to ionize as well. It ionizes incompletely. Most of the molecules will end up in that state. So this one's going to react. So we have CO3 2 minus, the carbonate ion, and hydrolyze means reaction with water. So don't go putting in there H plus or OH minus. It is hydrolysis. It's reacting with water. So the whole water molecule goes there. And what happens is a hydrogen ion, an H plus a proton, is donated from there to there. And then we end up with HCO3. Now it's only minus because it was 2 minus and it received an H plus, right? And then what will happen to the water if it gives off an H plus? It means that will end up with OH minus, and that is why the solution is turning basic, right? Because the carbonate is reacting with the water, it is producing OH minus. But that is still not an answer because we're looking for an acidic solution. So that must be the last one, but let's just check. So for the last one, you've got ammonium and you've got chloride. And the ammonium reminds us of ammonia, and that reminds us of HCl. So those two together would have produced a solution of ammonium chloride. Now, what do I know about ammonia? That is a weak base, right? And that makes the conjugated acid a strong acid. So that one is going to react with water. Right, how about Cl minus? Cl minus come from the strong acid HCl. So this is a weak conjugated base, and it will not react. So if it comes from a strong one, it will not be reacting because the strong ones want to be ionized or dissociated if you were a base, looking for a base. Right, so we've got a weak base and a strong acid. So the acid is winning. This will be an acidic solution. But if I have to tell them why it's acidic, I will say the ammonia ion will react with water, right, to form NH3, and it does that by donating a proton, right? And then we end up with H3O plus, and that is why the solution is acidic. Right, so the answer there was D. Right, moving on. Next one, consider the following two solutions. Now, you've got the hydrochloric acid there, that is the strong acid, and that tells us it will ionize completely. And ionize completely means every single molecule of HCl will react and will ionize. And that means every HCl will produce a hydronium ion, and immediately the concentration of that hydronium ions will therefore also be 0.1 moles per cube decimeter. Then we look at acetic acid or ethanoic acid. Now, what do we know? That is a weak acid, right? So that tells me this one ionized incompletely. And if it ionizes incompletely, it means only some of the molecules will ionize. Most of them will stay in their original molecule form, right? Only some of them will ionize. And that means the H3O plus that you are making will be less than 0.1 moles per cube decimeter, because not everyone is making an ion, right? And that immediately tells me the highest will be HCl, and then the higher the hydronium ion, the smaller the pH, right? And that tells me I'm looking at B. Last one there, which of the following 0.2 mole per cube decimeter solutions has the smallest pH? Now they've all got the same concentration, so it is, what do? How do they ionize? Now, ethanoic acid, CH3COOH, what do I know? This is a weak acid. It will only ionize incompletely, right? What do we know about nitric, HNO3? That is a strong one. That will ionize completely. Carbonic acid, H2CO3, weak. ionize incompletely, and sulfuric acid, H2SO4, strong, and ionize completely. So the weak ones we are immediately going to throw away, because the weak ones are only going to produce a few hydronium ions, right? So they will not give me the smallest pH, the most acidic solution, right? Then I'm looking at nitric acid and sulfuric acid. What is the difference? Well, nitric acid is monoprotic and sulfuric acid is diprotic. That means that one that is monoprotic, giving off one proton, is going to have an H3O plus concentration of 0.2 moles per cube decimeter, because every single HNO3 will react. It's strong, it ionizes completely, and every one of them will produce one H3O plus, right? But when we get to this one, it's strong, it will ionize completely, but if you look at it, you will see it is diprotic, meaning for every H2SO4, I will have 2 hydronium ions formed. And that tells me the hydronium ion concentration here will be 2 times 0,2, which is 0,4 moles per cube decimeter, which is definitely more, right? It's diprotic, it's giving 2 protons for every sulfuric acid molecule. Now we're going to look at longer questions. Now the first one there, 6.1. In an experiment, 0,02 moles of a monoprotic acid HR reacts with 200 cube centimeters of water. Write an equation. Right, write an equation. Now, immediately I know that this is an acid, and what do I know about acids? It ionizes, right? So we need water in our equation, and it ionizes by being a proton donor. So an H plus will be given off, and that means that will end up as R minus, and the water gaining that H plus is now H3O plus. You get the hydronium ion there, and that one will be in solution, that one will be in solution, this one is a liquid, and this one I don't know. Right, they didn't tell me. Moving on to number B, what type of a reaction? Now, this is an acid, and we know acids ionize, so it's ionization because it makes ions by reacting with the water, right? Next up, calculate the concentration of the HR solution. So we're looking for concentration, and we already have moles, and we already have volume over there. So this is easy, moles per volume, 0.02 divided by volume. What's the catch? It must be in cubed decimeters, right? So that ends up being 0.2, and I end up with 0.1 moles per cube decimeter. So that is my HR concentration. And now they ask us, if they do this and they go and measure, they find out that the hydronium ion concentration is 3.1 times 10 to the minus 7, and they ask us, is this a strong acid? Now first, what is a strong acid? The definition of a strong acid, it ionizes completely, right? So if I put 0,1 moles in every cube decimeter, in every liter, if I put 0,1 in, and it ionized completely, which means every single molecule reacted, I should have had 0.1 as well, right? But I don't have that. What do I have? I have 3.1 times 10 to the 7, 0,1, 2, 3, 4, 5, 6, 3, 1, right? That is a lot smaller, which tells me that most of the HR molecules did not ionize, right? So when they ask me, is this a strong acid? I will say, no, it's definitely not a strong acid. How do I know that? Because the hydronium ions that were produced is a lot less than the HR molecules that I started with. And therefore, I can say it ionizes incompletely. So remember in your answer to refer back to that definition. Okay. Right, moving on to 6.2. They tell us a sodium hydroxide, NaOH. What do I know about NaOH? Strong base, right? Strong base solution is prepared by dissolving 1.5 grams. So they give us a mass of hydroxide pellets in a water volume. Okay, so they give me volume as well. And they're asking pH. Now, in the videos, we talked about the relationships between all of these, right? We are now looking at a strong base, right? And they're giving us mass and volume, and we work towards pH. So we have to end at pH. Now, to get to pH, I need the hydronium ion concentration. And that, from a base, will be, I'll have to take the concentration of the base and first get the OH minus and then convert that to the H3O plus, right? If I'm in a watery solution, that equation is the one that's going to tell me if I've got the OH minus, how much H plus I'm going to have. So first off, I'm going to start to calculate the concentration of the base and then use that to get the OH minus, right? And then use that to get the H3O plus and then use the pH. So there's a few steps, but it's not difficult, right? We're starting off with that one, 6.2. First off, I want the concentration, right? So concentration is mass divided by molar mass times volume. On the information sheet, mass 1.5. Molar mass, we're working with sodium hydroxide, 2316, it's 40 times, and the catch, remember the volume, you must convert to cube decimeters. So that ends up being 0.5 down there. And that will give you 0.075 moles per cube decimeter. Right, that is the concentration of the NaOH. Right, so I now have the concentration of my base, and it's a strong base. So what do I know? Strong base, it dissociates completely. And if I look at sodium hydroxide, every single sodium hydroxide molecule will give me one OH minus. So NaOH is a strong base, and that tells me it will dissociates completely. Every single molecule, formula unit will react. And what do I know? Every NaOH will give me one OH minus. They're in the ratio 1:1. So immediately, if I have the NaOH and everyone is producing one OH, it means the OH minus concentration is the same. It's also 0.075 moles per cube decimeter. Now guys, sometimes you think 1:1, you don't have to show this. You have to show it. It could have been 1:2, right? Now usually, for instance, we take magnesium hydroxide. Magnesium hydroxide is usually considered a weak base, right? But they can tell you, assume that it dissociates completely. Then it will be 1:2. So you need to show the 1:1 because it could have been something else, right? Now I've got the OH minus. How do I go from OH minus to pH? For pH, I need the hydronium ion, right? But I've got OH minus. So that is the Kw expression. Kw equals OH minus times H3O plus, right? Now Kw is a Kc, it's an equilibrium constant. We're going to use 1.10 to the minus 14 because we assume we are at 25 degrees Celsius, right? And that being 0.075, that will give us the hydronium ion concentration, right? So I end up with the H3O plus being that divided by that, and I end up with 1.33 times 10 to the minus 13. And remember, pH doesn't have a unit, but concentration does. Mole per cube decimeters, right? And then I can put it into my pH calculation. Negative the log of the H3O plus concentration, and that is negative the log of 1.33 times 10 to the minus 13, and I end up with 12.87. Right. Let's look at the next one. Now the next one is the other way around. I'll talk about pH soon, pOH soon, for guys who are going to try to use that. Right, next one, they ask us an unknown amount of NaOH is dissolved in, so give us a volume, and the solution has a pH of that, so they give us pH. And then they ask calculate the mass. So we are actually doing what we do here, but we're doing it the other way around. We're starting from pH, right? Now, when you start with pH, we'll say 6.3, pH is negative the log of the H3O plus concentration, and that is now 12,2. Right. How do I get rid of that minus? I take it over to the other side, multiply on both sides, then I have minus 12,2 is log of H3O plus. And how do I get rid of this log? I have to put 10 to the power of 12,2, and that will be equal to H3O plus. Right, so I can just put it into my calculator like that, or you can put it inverse, right? Second function log of minus, and that's the one you forget, second function log of minus 12,2, or 10 to the power of minus 12. And don't leave it like that, right? That's not acceptable. You really have to work it out. And if you go and work that out, you will end up with, let me just check, right, 6,31 times 10 to the minus 13, and once again, moles per cube decimeters, right? So the only thing that pH can give you is H3O plus. And then we are working towards a base, right? So I'm looking towards OH minus. So the next one is doing the KW to say H3O plus OH minus. So this is 1 times 10 to the minus 14 equal to 6,31 times 10 to the minus 13, and then my OH minus, right? And that gives you an OH minus concentration of 1,58 times 10 to the minus 2 moles per cube decimeter. Right, so what do I have? OH minus, but I want to have not the OH minus, but the sodium hydroxide. So how do I go back? Well, sodium hydroxide is a strong base, which immediately tells me this will dissociate completely. And if I look at it, I can see that 1 sodium hydroxide will produce 1 OH minus. They're in the ratio 1 to 2, and you have to show that, right? Okay, so now if the OH minuses were 1,58 times 10 to the minus 2, and every one of the OHs was produced by 1 sodium hydroxide, it immediately tells me the sodium hydroxide concentration is also 1,58 times 10 to the minus 2 moles per cube decimeter, right? But they're not asking concentration, they want mass. So once again, we're going to use C equals M over M times V, right? Concentration 1,58 times 10 to the minus 2. We're looking for the mass, molar mass 40, and volume, they've given us the volume, and that was 0,25, right? And I end up with 0,158 grams. Right, so guys, you end up with 0,158. You may round that to 0,16, okay, or you can leave it like that, a minimum of 2 digits after the comma. Right, moving. We've now done this. We worked from pH back to our mass, or we worked from mass to our pH. Now, some of you guys have teachers that use pOH. Now, the reason why I haven't used pOH is that is actually not in the CAPS document, right? But I think they will take it as correct. So you can, from the OH minus, you can get the pOH, right? Which is just pOH is just negative the log of the OH minus. And then from pH, you can go to pH by saying 14 equals pH plus P OH. Right, so that one is quite equivalent to that one, because that was 1 times 10 to the minus 14, right? You can see where it comes from. So you can do that, take the pH, get the OH to get the POH to get the OH, but I would prefer rather not to use that since it's not in the CAPS document. Right, guys, this is all for today. Next week, we'll be looking at more interesting questions on acids and bases, and remember to send us some. Right.